Okay, thank you, Raul. Well, thank you for the invitation, for many years of collaborations and so on. Always a pleasure to be here around. Today I present a work with that started as a master project of Nathan Schaffer, also in collaboration with Matteo Raviola, who then took over and finalized this work.
Just keep it from the top. Yeah,
yeah.
Speak louder. That's it.
So it's about some improvement on stochastic gradients that we have proposed using control variates. Yeah, that's essentially the outline of the talk. Let me skip this. So the focus is on stochastic optimization. So we want to minimize. Let's say we have a cost function g. U is the design variable. The cost function depends on some random variables y, and we want to minimize the expected cost. So we assume that we know the distribution of this randomness y, and we can sample from y. And the design U lives in some Hilbert space to be finite or infinite dimension. The underlying, so what we are actually targeting are PDE-constrained optimization problems. So situations where evaluating G is very costly, typically involves simulating a complex model, partial differential equation, or something like this. So we really want to minimize the number of queries of the function G or the gradient of the function G. In terms of theoretical results that I will present, we have only analyzed the nicest case of a strongly convex functional. Doesn't mean that the method cannot be applied outside of this. It's just that the theory is available at the moment under this strong assumption. So I assume that G is continuously differentiable in U. And we can actually differentiate under the expectation, so we can compute the gradient of J as the expectation of the gradient of G. That's a nice feature. I assume that G is Lipschitz continuous. The gradient of G is Lipschitz continuous in U, with a Lipschitz constant that may depend on the randomness, but this constant is square integrable with respect to the underlying measure. And J is strongly convex with a convexity constant alpha. And I should also say that we are working on the, let's say, well-conditioned case where the ratio L over alpha is not too big. So we have not looked at that preconditioning of the gradient descent. So under this nice setting, there exists a unique optimal solution U star, which minimizes the functional J and is the unique stationary point of J. So just after the stationary point of the function J. All right, so a reference method is a gradient descent. As I said, in the well-conditioned case, the gradient descent is a good method. Where we just take the gradient step in the gradient direction of the function J with a fixed learning rate tau. And this gradient descent method converges linearly or geometrically, it depends on the community you're in. So it means that the error is reduced by some factor k at every iteration. Gamma being smaller than 1. Of course, this is not a directly viable method because computing the gradient of J implies estimating an expectation, which is not directly computable. And I forgot to say that we're in particular looking at the case where Y is a continuous random variable. So this is not just a finite sum, it's a whole integral. So if you want to apply the gradient descent method, you have to approximate this expectation, and this may become extremely costly, given that evaluating G is costly. So, of course, another very popular idea is the stochastic gradient, where you replace the true expectation with unbiased but relatively cheap estimator of the gradient. So it's very simple equation. You just take one realization of the random variable y at each iteration, independently from the previous rows, and you just use this as an estimator of the gradient. So it's unbiased, but the variance is not small; it's of 1. But the variance is scaled over the iterations because you iterate a lot in this setting. So you achieve, or you can also use a mini batch. But again, the idea is not to have necessarily a small variance. So then the convergence is achieved by shrinking the learning rate over the iterations. So the nice feature of this method is that you have a unit cost per iteration. So you only have to do one evaluation or very few evaluations per iteration. But of course, the convergence is much slower and is only 1/k in mean square seconds. So somehow you lose this nice exponential convergence of the gradient. So then the question is, could we recover a better convergence if we somehow exploit the history of the gradient evaluation? So let's try to build a control variate or to improve this gradient estimator using past information. And actually, there are several ideas that have been proposed. One of those is actually the mice method that Raul has presented yesterday. So all the authors are here, almost all the authors are here in this room. There are others, the SAGA, the SVRG, quite a few contributions that goes in this direction that try to learn somehow the gradient using past information to improve this estimation of the gradient. So the work that I'm presenting actually starts from this idea of SAGA and tries to improve this idea of SAGA. By the way, I forgot to say that and those of you who were at the MCM conference might have seen this presented by Matteo there. So it's just exactly the same work. So what does SAGA do? This is a very brief recap. The first SAGA was designed in the case where y is a discrete random variable. So this expectation is a finite sum. And then the idea of SAGA is somehow to build a control variate that works in this way. So the idea is to store the gradient of G, or let's say the most recent evaluation of the gradient of G for every possible outcome of this discrete random variable y. So you have a big table, psi k, that contains all these gradients estimations for each one of these outcomes. Of course, those come from the past, so they are not all taken at the current value of u. So they are taken at previous values of u. So somehow this inconsistent estimation. But the idea is that u is convergent, uk in the iteration is converging to the optimal value, and then you refresh this memory. So eventually this table becomes more and more consistent with the true gradient in all points yj. Of course, you have to initialize this table somehow, either to 0 or to the gradient evaluated in a single point. So you initialize in some way. And then the algorithm works like this. At each iteration, you draw an index 1 to s, again, independently from the past, and you evaluate the gradient for this outcome of the random variable. And then you use whatever you have in memory as a control variate for this. So this is your estimation of the gradient in this current point. You compare with whatever you have in memory. Now you have to have an unbiased estimator. You have to sum the expected value of this control variate, which is just the sum, the average, sample average of all your estimations in the memory. Okay, so this is an unbiased estimator because of the random draw of the index, uniform random draw of the index. And then once you have done your gradient update, then you update the memory because you have a new evaluation of the gradient. So in this position here, you put the new evaluation and you throw away the old one. So then the memory gets refreshed every time you have a new gradient estimation. It get better and better, and essentially you achieve a better and better control variate. That's the idea of the SAGA, and actually the authors of the SAGA, the paper is from 2014. They show that they can recover this geometric or exponential convergence for this method here. So notice that the cost is just one evaluation per iteration. So the same cost of the plain stochastic gradient. Of course, then there is a big overhead, not in the cost, but in the memory storage, because you have to keep in memory this table. And if S is very large, this could be quite demanding. But so there is a big memory cost. That's somehow the first limitation of the SAGA. And there is also another limitation is that, as a matter of fact, this gamma here scales like 1 minus 1 over S. So if the number of possible outcomes of your random variable is very large, then yes, you do recover a geometric convergence, but it will become slower and slower when S increases. As I said, this was somehow the starting point. So we did use in this previous work with Mathieu Martin this idea in the context of PDE-constrained optimal control problems, where Y is a continuous random variable, let's say PDE with random coefficients, and then we want to optimize something. In that case, we just approximated this expectation with accurate quadrature, let's say tensor product Gaussian quadrature. You have a lot of points, you have the curse of dimensionality, but now it becomes a discrete sum, and then we apply SAGA on this. And then you may also question whether you should draw uniformly or you should draw the points according to the quadrature weights, and so we have analyzed this aspect as well. But still, you have to upfront decide how to discretize this expectation, and you still have this degeneracy, at least in the proof, and also in the numerics, we saw that you still have this degeneracy with 1 minus 1 over S. It means that if you draw your quadrature too big, then SAGA will suffer because you have too many states to explore, keep in memory, and to refresh. So it will take a lot of iterations to refresh the whole memory. So this impacts the convergence. So with Matteo, we started discussing, well, can we do a version of SAGA that is more suited for continuous random variables? So we don't need this upfront discretization of the expectation. And this is a general idea that, so we call it memory-based control variate. So say, okay, instead of discretizing the expectation, we could try to build a model, K, that is an approximation of this gradient of G somehow. Okay, and this model should be updated at every iteration based on the evaluations of the gradient that you have. Well, let's say that somehow we come up with a reasonable model. So what I will discuss today is actually a model that is based on least polynomial, so least squares on polynomial spaces. So again, under the assumption that this map from Y to G is a smooth map, we can approximate with polynomials, maybe using discrete least squares. So let's try to build a model in this way. Okay. We have a model that uses at iteration K, Sk gradient evaluations from the past, from the history. You could use all of them or just some of them, so the most recent ones. Again, it could be a regression model, it could be a kernel interpolant, it could be a Gaussian process, you can imagine many different situations. I will discuss the first one. And the assumption, the underlying assumption is that since you want to use it as a control variate, you have to be able to compute the expectation exactly or very accurately and cheaply. Okay. So the expectation, okay, that's a conditional expectation because the model decay is built from the past, but then you evaluate on a new independent realization of the random variables, so you have to be able to compute this conditional expectation even though the past situations. So as I said, the model is built using this memory. So the memory is a collection of all the YJ evaluations and the corresponding gradient estimations that you have in the history. Those, as I said, exactly as in SAGA, these gradient estimators, they are not consistent because they are all evaluated in different UJ. So ideally, this model should be a model for the gradient evaluated in the current state UK, but you cannot afford to reevaluate all the gradients in the current, so you just use the previous one, even though they are evaluated on different points, and you rely on the fact that this sequence UJ should converge to the optimum. So this model becomes more and more consistent when you go over the iterations. And of course, you have to initialize somehow the memory and the model. Okay, and then the algorithm is quite straightforward. So at each iteration, we draw a new random variable yk independently from the past, and then we build this control variate estimation of the gradient. So we evaluate the gradient with the current outcome of the random variable and the current estimate of the design UK, and then we subtract the model evaluated in the same point, and then we sum the respective conditional expectation of the model, given the filtration. And then we update the memory. Now we have a new gradient estimation, so we add this to the memory. Eventually, we throw away all the estimates if we want to keep the memory size fixed. Okay. This estimator is again unbiased, conditionally unbiased. Conditionally in the past is an unbiased estimate, so it's the same properties as the one on stochastic. So that's the first idea. Of course, we can add an important sampling strategy. This will be relevant for least squares. So if you want to build a least square model and a stable least square model, maybe you don't want to sample from the original distribution. Maybe you want to sample from a different distribution that makes this least square more robust. Okay, and this can be done quite easily. You just add an important sampling to this estimator. So let's say that for some reasons you want to sample from a different distribution, mu instead of rho. Okay, you can do this, and then you have to correct your estimator with a likelihood ratio 0 over d mu. Okay, so it's not a big deal. What those of you who are familiar with the optimal squares, they get already where I'm heading to. If somehow you want to improve the model over the iterations, let's say if you do polynomial approximation, you might want to enrich to get a larger and larger polynomial space. The more evaluations you have, this might imply that this optimal sampling measure may change over the iteration as well. Okay. So this is a little bit more tricky how to handle this. The way we propose is the following. So let's suppose that to build a model at iteration k, we select a certain dictionary, and then we do least square on this dictionary. And for this, we would like to have the points y drawn from this measure mu k at iteration k. But this mu k is changing from one iteration to the other. So one idea is if I can write, so let's say I go to iteration k plus 1, if I can write the new measure mu k plus 1 as a mixture of the old measure plus the correction term, a simple fix is to do a resampling of the memory, where you say, okay, the memory is doubly inconsistent. It's inconsistent because the gradients are evaluated on wrong points, but it's also inconsistent because the yj are not taken from the right measure. But since I have this mixing structure, what I can go is go through all the memory, draw a Bernoulli random variable with parameter alpha k. If alpha k is 1, so I'm drawing from this, so it means I don't have to change the memory. So the y has already the right distribution. If my Bernoulli is 0, then I throw away what I have in memory and have to redraw now from this other correcting distribution. So it does have some extra cost because I might need to reevaluate some terms in the memory in the old point uj, or you could keep the old point, or you could use the new point, the latest point uk, so that your memory is consistent with the new sampling distribution.
You can take questions now. So the mu k, is it changing just in the beginning, but then it stabilizes, right? If the sk is not changing with
if you no. If in the case I will discuss later, where you increase the polynomial space, the more iteration you have, the more gradient evaluations you have, the larger polynomial space you can take. This means that you increase the polynomial space, you increase the memory size, and you change the sampling measure at every iteration.
So you never throw away the initial samples.
We do, because taking all the gradient estimations is, let's say, increasing as much as you can the polynomial space while keeping a stable reconstruction is a too aggressive approach. So you have to increase a little bit slower than the iterations of the stochastic gradient. That's what we're observing.
So just to follow up on that, so the samples here are just for the stable reconstruction, meaning that all components of the gradient are essentially using the same subspace, or?
Yes.
Because otherwise it gets very messy, right?
Yes, what we did is use the same subspace for a component of the gradient, absolutely. It could be...
It would be very messy.
It would be very messy, but there are some clever idea
only if there are very big scales of the difference in the stochastic components of the gradient. Otherwise, it's not worth it.
Okay, so I recalled I call this resampling on the memory with this RSK. Add this resampling step. Okay. And of course, it implies some extra cost to this extra evaluation of the gradients to keep the memory consistent. So least squares now. I guess many of you are familiar with least squares and optimal least squares. So the idea here is to take a sequence of subspaces. In particular, we work with polynomial subspaces, but this is not strictly necessary. And I assume that this sequence is dense in L2 gamma, and the subspace Bm has dimension m. And so we want to do this reconstruction of the gradient in this space Bm. Iteration k, we use the space bmk with a certain memory sk, and that's just the standard least square. Well, weighted least square because the y's are drawn from this measure mu k, but you want to minimize the L2 row error So you have this again slightly ratio when you build a weighted least square. Okay. So that's the reconstruction step. Yeah, the tilde here means that those are the redrawn samples to keep the consistency. So what is known about this weighted least square has been quite well studied, and what I'm using here is the version proposed by Cohen and Migliorati in 2018. So if you have an orthonormal basis, so this works particularly well when you have explicitly an orthonormal basis for this space VM. I call it phi I. So you draw samples from a distribution mu. You build this. So here I write it for a generic function psi. In practice, this will be the gradient of G. So this is a quadratic minimization problem. So it's very easy to solve. It just leads to a linear system. This linear system has a matrix G, which is a Gramian matrix. So the basis functions evaluated in a sampling point with the weight, which is weighted least square. So the question is whether this system is well conditioned. Now in expectation, the y's are distributed according to mu. So when I take expectation with respect to the distribution of y, I get the L2 row inner product, but my basis is orthonormal. So in expectation, this is the identity. And actually G is the sum of is the sample average of IID matrices. So you do expect this to concentrate around the identity if you use enough points, S large enough. And that's the main tool to analyze the convergence and stability of this reconstruction method. So the result from the paper by Cohen and Migliorati says that, sorry, small correction. What this analysis says is that with high probability, since G is concentrating around the identity, with high probability, G is well conditioned. But of course, there might be cases where G is ill-conditioned, so we can fix this projection by saying that if the matrix is too ill-conditioned, we just take 0. So 0, of course, is a totally wrong reconstruction, but this happens with very small probabilities, so shouldn't impact too much. So I call pi tilde this corrected reconstruction. So what can we say on this? Actually, the result says that if you satisfy a certain sampling inequality, so if the sample size S is large enough, you have that in mean square sense, the error, the reconstruction error is up to a well-behaving constant, which is roughly 1 or over 1, equivalent to the best approximation error. So the best reconstruction that you can do in the subspace VM, so the exact L2 projection, plus a small term, and the small term comes from this small probability of failure of the reconstruction. Okay, and the sampling inequality is this one, which involves this strange quantity kappa. It's related to the Christoffel or inverse of the Christoffel function. Essentially, it's the supremum of the sum of all the basis functions squared. Okay. So question is this kappa big or small? Well, it's not difficult to say that this kappa is lower bounded by m, or less, so greater or equal than m. And actually, you can make it equal to m if you sample exactly from this distribution here. So if you sample from, this is a probability distribution because it's positive and integrates to 1. So if you sample from this distribution here, it's very easy to see that this kappa becomes exactly 1 because this Platonic derivative is exactly this template. Okay, so that's what we call the optimal sampling measure. Optimal in the sense that it makes this sampling inequality the less stringent possible. So it's not optimal in the sense of error, but it's optimal in the sense of stability of reconstruction. But the point is that this optimal measure does depend on the subspace that you choose, because you are taking the sum of all the basis functions. So if you take a larger subspace, your sampling measure is changing. Okay. So if you take the optimal one, which by the way is a mixture, so you can sample as a mixture, you draw an index, and then you have to sample from this squared basis function somehow. If you take the optimal one, you have a sampling inequality that roughly says that S up to log term, S should be of the order of M. So you have to do a little bit of oversampling, but not too much to keep stability. So M is the dimension of the space. So if you want to reconstruct a polynomial with 10 terms, you need maybe 20 samples, and you get stable and accurate reconstruction. Okay? And this optimal sampling measure, you can write it as this mixture, because if you have, if you go from Vm to Vp, P being larger than M, you can always write the optimal sampling measure in Vp as the optimal sampling measure in Vm up to vector M over P, plus a correction which involves all the basis functions which are in Vp but not in Vm. Okay, so it does have this mixture structure, which means that you can do this sampling of the you might work with a quasi-optimal sampling measure that is somehow equivalent to the optimal one. This might have some advantages, because for certain cases you can come up with a fixed mu that is quasi-optimal for all subspaces, and then the advantage is that it doesn't depend on the subspace anymore, so you can keep your measure fixed. That's the case, for instance, for uniform random variable and the Legendre polynomials. The arc sign distribution is quasi-optimal, so you can work with the arc sign distribution, and you will have a stable reconstruction in 1D. So that's the algorithm for this least square reconstruction. So we collect gradient estimations, we do this least square reconstruction, and then we use this as a control variate with important sampling, because we want to sample from a good sampling measure, which is not necessarily the original raw measure. Okay, so what were we able to prove? Should be careful with time. How much?
I checked. 8 minutes.
So what were we able to prove in the strongly convex setting? So we first analyzed the case where we used the fixed subspace in this reconstruction, which means so the size and the basis functions in the space do not change, the sampling measure doesn't change, the memory size doesn't change, so that's an easier setting. And we have analyzed this algorithm with a fixed learning rate. Now, since the variance of the estimator doesn't go to 0, because with a fixed subspace we cannot approximate exactly the gradient, if we don't shrink the learning rate, we will not converge. We will have a bias in the limit, but the bias is of the order of the approximation of the gradient that we are doing. So that's what this result says. So we look at the error at iteration k plus 1, conditional on the past. This will be proportional to the previous error times factor smaller than 1, plus 2 other error contributions, A and B. They are both scaled by tau square, the learning rate square. So what we are doing here, so we are using this reconstruction based on the history. Now, for error analysis, we want to compare this with the ideal reconstruction, assuming that all the gradients are evaluated in the optimum. Okay, that would be a consistent reconstruction with the optimum. So we sum and subtract, let's say, the ideal reconstruction, and then we have to also we can split the error with 2 contributions. One precisely compares the reconstruction that uses the history with the ideal reconstruction where all the gradients are consistently estimated at the optimum. And the other is just the reconstruction, the optimal reconstruction compared to the 2 gradients. This is the approximation error due to least squares. Will decay at a certain rate depending on the size of the subspace and depending on the smoothness of the gradient. So that's the term that depends on the least square approximation. Well, the first term is trickier to analyze. I mean, it can probably be analyzed in different ways. What we did is the most naive way. So since this reconstruction involves the whole history, and we assume Lipschitz continuity on the gradient, somehow this can be related to the sum of all previous error contributions up to k minus s. Okay, so this becomes an S-term recursion instead of a one-step recursion. It becomes an S-step recursion because of this memory effect. Okay, so this is the type of estimate that we have. So the error k plus 1 depends on the error k times a factor smaller than 1 plus this sum of the previous S errors scaled by tau squared plus this term here, which is the best approximation of the gradient in the subspace against scaled by tau squared. Okay, and then it's a pain to work out this recursion. That Matteo did a great job on that. So he was able to show that if you keep a fixed learning rate, there does exist a gamma smaller than 1 for which you have this geometric convergence up to this best approximation error. Again, this is a biased estimation, so you will have this error at the end. And just a little technical point, which I'm not sure is improvable. Here in this estimate, there is a Q appearing, and the Q is the supremum of this radon-nicotine derivative, which is something that could, if you increase the subspace, this is something that could blow up. So one has to control how fast this term is actually going up.
Optimal has a constant that depends on the dimension, right? Is it because of that?
No, if this measure is fixed, this is just a number. But if you increase the subspace, if you have a fixed quasi-optimal measure, that's fine. If you don't have a fixed quasi-optimal measure and you want to use the optimal measure, then this mu depends on k, and then this q depends on k, and it will or might blow up over the iterations. But the hope is that it goes up mildly and it's compensated by this term. So it was fixed subspace, and it's actually similar to SAGA in the sense that this gamma is actually 1 minus 1 over s. So it's similar. S is the size of the memory. You know? So it's a very similar result to SAGA. Now, more interesting is the case where we increase the subspace over the iterations. In this case, we hope we can kill the bias because we collect more and more gradient estimations. We can do a better and better reconstruction. So in the limit, the control variate should become exact and the variance of the estimator should go to 0. Okay. So we have a certain scheduling functions. So how do we increase the size of the subspace over the iterations? Then we have to we choose an optimal or quasi-optimal sampling measure according to the subspace that we have iteration k, and also we take a memory size so that we satisfy the sampling inequality that gives a stable reconstruction. What could we show again here? So we worked out good choices of how to increase the memory size over the iterations, how to increase the memory size and the size of the subspace are linked by this sampling inequality, but also how to decrease it seems that there is an optimal decrease of the learning rate to get the fastest convergence. So we have analyzed the 2 different cases where the gradient, so the approximation of the gradient in the subspace of dimension m is exponentially converging with respect to the dimension of the subspace. Let's say your gradient is an analytic function in the variable y, and then by polynomials you can approximate it exponentially fast. This QK blows up algebraically. This is what we know. For uniform random variables, we know that we have a quasi-optimal sampling measure that is fixed, so there is no blow up. But for Gaussian random variables, we have to use the optimal sampling measure, and then this blow up is of the type square root of n, so it's relatively mild. So for the sub-exponential convergence, we came up with this choice. So the learning rate should decrease as 1 over k to the 2/3. So 2/3 seems to be this magic exponent. And the memory should increase as k to the 2/3. So it's sublinear. So you don't use all history. You grow slower than the iteration counter. And with this choice, we were able to show that the error decays sub-exponentially. So it's exponential to the minus k to the 1/3. Okay. Up to some right points. As an exponential case, the algebraic case, if we assume that the approximation error is algebraic, so n to the minus eta for some constant eta, and again this supreme may blow up as n to the psi, then it seems that the optimal choice is the stochastic gradient, is the Robbins-Monroe, so learning rate decays as 1 over k, and the memory increases k. So you almost use all the history to do this reconstruction. So you almost increase as much as you can up to log terms. In this case, the error decays algebraically as k to the minus 2 eta minus 1 plus k plus psi. So this psi is due to this degeneracy here. But if you forget this psi, this would be somehow the optimal rate due to this approximation here. This is a mean square error, so that's why there is a 2 eta here. And the minus 1 is because we're evaluating the expectation of the gradient. So the 2 eta rate is the L2 rate, but if you just look at the integration, we will get something. Okay, very briefly. Okay, so I'm out of time. So this is a numerical example where we apply to a PDE-constrained optimization problem. So this is a École problem where we have an analytic solution. So it's a diffusion equation with just one random variable, which is log uniformly distributed. And we try to minimize this. We minimize this cost function. So discrepancy between the solution of the PDE and certain target state, penalizing the control being the right-hand side of the PDE. We try to find the right-hand side in the PDE so that we minimize this mismatch with the target. And if we take the target as being an eigenvalue of the Laplacian, we have an explicit solution, so it's very convenient to analyze the convergence. In this case, it's one random variable, so we used one uniform random variable, so we used the Legendre polynomials to do this least squares, this reconstruction. And this is what the results that we obtained. So this is for fixed subspace. You see that you have a nice exponential convergence in the number of iterations until you hit the approximation power of the least squares. Okay, so if you take a larger subspace, you will have a slightly slower convergence, but of course, the bias is reduced. But then if we do the increasing subspace with the rule that I presented, then we nicely converge up to machine precision over the iterations. The green one is a SAGA, which in this example also performs well, but you have to choose again how many points. So here we use 20 Gauss points, and then the convergence is lower. If we had used the fewer points, the convergence would be faster, but at some point you saturate due to the error in the quadrature. So again, you have to decide what quadrature to use, and whereas this is more adaptive over the equations. This is a slightly more challenging example. Is a diffusion transport equation with 5 random variables parameterizing the transport field, the diffusion, and the right-hand side, where we minimize the norm of the solution of the PDE. In this case, we used a priori, I mean, it might not be the best choice, but we used a sequence of hyperbolic cross polynomial spaces in 5 dimensions, adapting and increasing the size of all the iterations. The results are much more noisy, but similar to before. So if we fix the approximation phase, we see that the larger the spaces, the slower would be the convergence, but you have a smaller bias. And if you increase the approximation space over the iterations, you eventually converge to the output. Okay, stop here. Thank you for your attention. So this is the very recent paper on archive. That's the older one on SAGA.